Welcome to Sleepy Science Post, where we explore the wonders of our natural world through gentle storytelling designed to ease your mind into peaceful rest. Tonight, we embark on a slow, meditative journey through the silent world of glaciers, those ancient rivers of ice that have shaped our planet for millions of years. Let their quiet majesty and timeless patience guide you towards sleep. A whisper of ancient ice. Close your eyes and imagine standing at the edge of the world, where time moves differently. The air is crisp and clean, carrying with it the faint scent of snow that has never melted. Before you stretches a landscape of pure white and blue, silent except for the occasional whisper of wind across ice. This is the realm of glaciers, Earth's slowest rivers, its coldest artists, its most patient sculptors. These frozen giants have witnessed the rise and fall of civilizations, the migration of species, the very shifting of continents. They hold within them memories of ancient atmospheres, bubbles of air from thousands of years ago, waiting to tell their stories. Tonight, we will listen to these stories, one gentle fact at a time, as we drift into the peaceful embrace of sleep. Let the glaciers be your guides. Let their stillness become your stillness. Let their ancient rhythm slow your breathing, calm your thoughts, and carry you softly into dreams. Fact 1: The birth of ice. Glaciers begin their lives not with drama, but with the quietest of processes, a single snowflake falling onto a mountainside. This snowflake doesn't melt when spring arrives. It stays, and another falls upon it, and another. Year after year, decade after decade, the snow accumulates in layers, each one pressing down on those below. The weight transforms the delicate crystalline structure of snow into something denser, something called neve or firn. This is not yet glacier ice, but it is becoming. It is patient. It has all the time in the world. Under pressure that builds over 30 to 40 years, the air pockets between snow crystals gradually compress and the snow recrystallizes into ice. A glacier is born not in a moment, but across lifetimes. Fact 2: The definition of patience. A glacier is officially defined as a large, persistent body of ice that forms on land and moves under its own weight. But this movement is invisible to the human eye in most cases. The fastest glaciers in the world might move 30 meters in a single day, but most glaciers travel only a few centimeters daily, about the rate your fingernails grow. Imagine a river so slow that you could spend your entire life watching one section, and barely perceive its journey. This is the pace of glacial time, a reminder that not everything in nature hurries. Some of Earth's most powerful forces take their time, reshaping entire landscapes through nothing more than persistent, gentle pressure applied over thousands of years. Fact 3: Colors of the frozen world. When you imagine ice, you might picture white or clear, but glaciers paint in a palette far more subtle and beautiful. The ice can be white where it contains many tiny air bubbles, each one scattering light in all directions. But as ice compresses over time and air bubbles are squeezed out, something magical happens: it begins to glow blue. This is not paint or reflection, but physics. The dense ice absorbs every color of light except blue, which bounces back to our eyes. The older and more compressed the ice, the deeper and richer the blue becomes, creating shades that seem to belong to another world entirely. Some glaciers also display bands of gray or black where they've picked up rock and sediment, and others show cream or yellow tints from ancient volcanic ash trapped within their layers. Fact 4. The weight of time. The ice in a glacier isn't distributed evenly, it forms in layers, like the pages of a history book written in frozen water. Each layer represents a single year's snowfall, and these layers are called annual layers or varves. Near the surface, these layers might be several meters thick, but deeper down, compressed by the enormous weight above, they can be compressed to just centimeters. Scientists can read these layers like tree rings, counting backward through time. In the deepest glaciers, ice near the bottom can be over 800,000 years old. Imagine that, water molecules that fell as snow before modern humans walked the earth, still frozen, still waiting, holding within them tiny bubbles of ancient atmosphere. Fact 5. The anatomy of a giant. Every glacier has a distinct anatomy, like a living being. At the top sits the accumulation zone, where snow falls and builds up faster than it melts. This is where the glacier feeds and grows. Lower down lies the ablation zone, where summer warmth causes more ice to melt than winter snow can replace. Between these two zones is the equilibrium line, a delicate balance point that shifts with climate. Glaciers also have crevasses, deep cracks that form when the ice moves over uneven bedrock or around curves. These crevasses can be hundreds of feet deep, and they create the maze-like surface that makes glaciers both beautiful and dangerous. At the very bottom of the glacier, where ice meets bedrock, there's often a thin layer of meltwater that acts as a lubricant, helping the massive ice sheet slide forward. Fact 6. Mountains of ice on land and sea. Glaciers come in many forms, each shaped by where it lives. Alpine or valley glaciers flow down mountain valleys like frozen rivers, carving deep U-shaped valleys as they go. Ice caps are dome-shaped glaciers that cover highlands and mountains, flowing outward in all directions from a central point. Piedmont glaciers form when steep valley glaciers spill onto flat plains, spreading out like pancake batter. And then there are the ice sheets, the true giants of the glacial world. Only two remain today, the Greenland ice sheet and the Antarctic ice sheet. These aren't just large, they're almost incomprehensibly vast. The Antarctic ice sheet covers an area larger than the United States and Mexico combined, and in places, the ice is nearly 3 miles thick. To stand on its surface is to stand on ice above buried mountain ranges you cannot see. Fact 7. The sound of silence. Most people imagine glaciers as places of absolute silence, and in many ways they are. There are no rustling leaves, no bird songs, no insect hums. But glaciers are not entirely quiet. They have their own subtle music. On calm days, you might hear the gentle drip of meltwater, the soft whisper of wind across ice, or the distant groan of ice shifting under its own weight. Sometimes, air bubbles trapped for thousands of years escape from melting ice with a sound like faint champagne fizz. And very occasionally, when a glacier moves across rough bedrock or when internal stresses build and release, it produces sounds that have been described as groans, cracks, or even musical tones. These are the glacier's voice, quiet and ancient, speaking in a language older than words. Fact 8. Temperature's frozen gradient. Not all glacier ice is the same temperature. Polar glaciers, found in the coldest regions, are frozen solid all the way to their base. The ice remains below freezing even where it touches bedrock. These glaciers are frozen in place, quite literally, and move extremely slowly. Temperate glaciers, found in warmer climates, have ice at the melting point throughout, especially at their base. This makes them much more dynamic, sliding more easily across their bedrock beds. Some glaciers are polythermal, meaning they're frozen at high elevations but temperate at lower elevations. This gradient of temperature creates different behaviors within the same glacier, the top moving slowly, the bottom flowing faster. It's like a river with currents at different speeds, all flowing together yet separately. Fact 9. The power of slow motion. Though glaciers move slowly, their power to reshape the land is immense. This power comes from three main processes working together over millennia. First is plucking, where the glacier freezes onto bedrock, and as it moves forward, it literally tears chunks of rock away from the ground. Second is abrasion, where rocks embedded in the bottom of the glacier act like sandpaper, grinding away at the bedrock beneath and creating a fine powder called glacial flour. Third is the sheer weight, millions of tons of ice pressing down, crushing and compressing everything beneath it. Together, these processes can carve through solid granite, creating valleys, fjords, and basins where none existed before. A glacier can cut through a mountain range given enough time, and it does so without hurry, without sound, with nothing but persistence. Fact 10. Valleys shaped like letters. If you've ever seen a river valley versus a glacial valley, you've witnessed the signature of ice. River valleys are V-shaped, carved by water rushing downhill, cutting a narrow path. But glacial valleys are U-shaped, broad, flat bottoms with steep, nearly vertical walls. This is because a glacier doesn't just cut through the bottom of a valley, it fills the entire space, grinding away at the sides as well as the bottom. When the ice finally retreats, it leaves behind these distinctive U-shaped valleys, which can be miles wide and thousands of feet deep. The Yosemite Valley in California is a perfect example, carved by glaciers that retreated about 15,000 years ago. The valley walls rise nearly 3,000 feet on either side, and the flat valley floor still bears the marks of the ice that shaped it. Fact 11. Lakes born from ice. Many of the world's most beautiful lakes were created by glaciers. There are several ways this happens, each one a different story of ice and stone. Some lakes form in cirques, bowl-shaped depressions carved high in mountains where glaciers first began to form. Others fill up glacially carved basins, deep holes scoured out where the ice was thickest or where it encountered softer rock. Kettle lakes form in a more unusual way. When a glacier retreats, sometimes large blocks of ice break off and get buried in sediment. When these ice blocks eventually melt, they leave behind circular depressions that fill with water. And then there are fjords, long, narrow inlets of seawater that filled glacially carved valleys when the ice retreated and sea levels rose. Norway's famous fjords can be over 4,000 feet deep, testament to how deeply glaciers once carved into the land. Fact 12. Mountains that float away. Glaciers don't just carve valleys, they can transform entire mountain ranges. Over hundreds of thousands of years, Glaciers grinding away at peaks create sharp ridges called arêtes and pyramid-shaped peaks called horns. The Matterhorn in the Alps is perhaps the most famous example, its distinctive pointed shape created by glaciers eroding away from all sides. Glaciers also create hanging valleys, smaller valleys that enter main valleys high up on the valley wall, often creating spectacular waterfalls as streams plunge down to the valley floor below. All of this happens grain by grain, boulder by boulder, century by century. Mountains that seem eternal to human eyes are, in glacial time, slowly being carried away to the sea, one meltwater stream at a time. Fact 13. The traveling stones. One of the most puzzling discoveries in geology was the presence of giant boulders in places where they clearly didn't belong. For example, a granite boulder sitting on limestone bedrock miles from any granite source. These are called glacial erratics, and they tell the story of ices carrying power. Glaciers can pick up rocks ranging from tiny pebbles to house-sized boulders and carry them for miles, sometimes hundreds of miles, before depositing them when the ice melts. The Olmsted Point in Yosemite has a famous erratic weighing several hundred tons. These out-of-place stones were once mysterious, but now we understand them as messages from the ice, proof that glaciers once covered lands now free of ice, and traveled far beyond their current boundaries. Fact 14. Striations, the glacier's signature. When you walk on bedrock that was once beneath a glacier, you might notice parallel scratches or grooves in the stone. These are glacial striations, created when rocks embedded in the ice scraped across the bedrock like a sculptor's tools. These striations aren't random, they all point in the same direction, showing exactly which way the glacier was moving, sometimes thousands of years ago. Some striations are barely visible hairline scratches, others are deep grooves you could fit your hand into. They're permanent records of ice's passage, signatures written in stone that will last millions of years. By mapping these striations across a landscape, scientists can reconstruct the flow of long-vanished ice sheets and understand how the land was shaped. Fact 15. Polished stone. In addition to scratching, glaciers also polish. Where the ice and its load of fine sediment moved across bedrock without larger rocks to gouge it, the result is glacially polished rock, stone buffed to a smooth, almost glassy finish. In some places, especially where resistant rock like granite was polished, the surface can still be smooth and shiny thousands of years after the ice retreated. You can run your hand across these surfaces and feel the smoothness created by ice, feel the touch of a glacier that existed long before human civilization. It's a tactile connection to deep time, proof that gentleness applied consistently can transform even the hardest stone. Fact 16. The debris it leaves behind. When glaciers retreat, they don't just leave behind shaped valleys, they leave enormous amounts of debris called glacial till. This is an unsorted mixture of clay, sand, gravel, and boulders, all jumbled together and deposited wherever the ice melted. Unlike river sediments, which are sorted by size and laid down in neat layers, glacial till is chaotic, tiny clay particles mixed with boulder-sized rocks, all compressed together. Glaciers also create distinctive landforms from this debris. Moraines are ridges of till pushed up at the front or sides of the glacier. Drumlins are elongated hills shaped like inverted spoons, formed beneath moving ice. Eskers are long, winding ridges of sand and gravel deposited by streams that flowed within or beneath the glacier. Each of these features tells part of the ice's story. Fact 17. Building soil from stone. In one of nature's slowest transformations, glaciers are soil makers. When a glacier grinds across bedrock, it creates glacial flour, rock powder so fine it can stay suspended in water for days, giving glacial meltwater rivers their distinctive milky appearance. This rock flour, mixed with organic matter over time, eventually becomes soil. Many of the world's most fertile farmlands, including much of the northern United States and Canada, owe their soil to glaciers that retreated only 10,000 to 15,000 years ago. The ice ground down the rock, and when it melted, it left behind a layer of mineral-rich sediment that, with the addition of plant matter and time, became the soil that now feeds millions. In this way, glaciers are farmers of the future, preparing the ground for life that will come thousands of years after they're gone. Fact 18. The glacier's blood. Though made of solid ice, every glacier has liquid water flowing through, beneath, and around it. During summer months, surface meltwater percolates down through crevasses and moulins, vertical shafts that can be dozens of meters deep. This water collects in channels and cavities at the glacier's base, forming an entire hidden drainage system. Sometimes these channels are large enough to walk through, cathedral-like spaces carved by water within ice. The water flowing at the glacier's base is crucial because it lubricates the ice's movement across bedrock. When more meltwater reaches the base, the glacier can surge forward more quickly. This internal plumbing system is complex and ever-changing, melting and reforming as the seasons shift, creating a dynamic environment within what seems like a static mass of ice. Fact 19. Glacial milk. Streams flowing from glaciers have a distinctive appearance, opaque and milky, usually in shades of gray, blue-gray, or turquoise. This is caused by glacial flour, the extremely fine rock powder created by the glacier grinding against bedrock. The particles are so tiny, sometimes only a few micrometers across, that they stay suspended in the water rather than settling out quickly. As light hits these suspended particles, it scatters, creating the milky appearance. Rivers fed by glaciers can carry this sediment for hundreds of miles before it finally settles out. When glacial meltwater enters the ocean, you can sometimes see the distinct color difference from above, a plume of pale blue-gray extending into the darker ocean waters, slowly dispersing as the sediment settles to the seafloor. Fact 20. Seasonal rhythms. Glaciers breathe with the seasons, though in slow motion. In winter, when temperatures drop and snowfall increases, glaciers gain mass. The accumulation zone grows, and the glacier thickens. In summer, melting accelerates, especially in the ablation zone. The glacier releases stored water, and its rivers run high. This annual cycle means that glaciers are never truly static, they're constantly adjusting to each season's changes. Scientists measure this with the glacier's mass balance, comparing how much ice and snow accumulates versus how much melts away. A positive mass balance means the glacier is growing, a negative one means it's shrinking. This balance is sensitive to climate, making glaciers excellent indicators of climate change, responding to shifts in temperature and precipitation over years and decades. Fact 21. Moulins, portals into ice. One of the most dramatic features on a glacier's surface is a moulin, a vertical shaft or tunnel through which surface meltwater drains down into the glacier's interior. The The word comes from the French word for mill, because the swirling water sounds like millstones grinding. Some moulins are only a few feet across, others are large enough to swallow a car. They can be hundreds of feet deep, spiraling down through blue ice to the glacier's base. Standing near a moulin, you can hear the roar of water plunging into darkness, see the mist rising from below, and glimpse the incredibly blue ice of the moulin's walls. These features are dangerous but mesmerizing, temporary structures that might last a season or several years before the ice deforms and closes them, only for new ones to form elsewhere. Fact 22. Subglacial lakes. Beneath some of the world's largest ice sheets lie hidden lakes, bodies of liquid water trapped between ice and bedrock. These subglacial lakes exist because the immense weight and insulating properties of the ice above keep the water from freezing, and in some cases, geothermal heat from below contributes additional warmth. Antarctica alone has over 400 known subglacial lakes, the largest being Lake Vostok, which is roughly the size of Lake Ontario and buried beneath 2.5 miles of ice. These lakes have been sealed off from the atmosphere for hundreds of thousands or even millions of years, creating unique environments that might harbor unusual forms of life adapted to extreme cold, darkness, and pressure. They represent some of Earth's last unexplored frontiers, hidden worlds of liquid water beneath a frozen ceiling. Fact 23. The ice that floats. When glaciers reach the ocean, several things can happen. Sometimes the ice simply melts as it enters warmer water. But in colder regions, the glacier can extend out over the water, forming a floating ice shelf or ice tongue. These features can be enormous. Antarctica's Ross ice shelf is roughly the size of France. Ice shelves are strange environments, neither fully glacier nor sea, but something in between. Beneath them, ocean water circulates, slowly melting the ice from below. Above, snow continues to accumulate, feeding the shelf with new ice. Eventually, under the stress of wind, waves, and tides, large sections break off, a process called calving, creating icebergs. But while attached, ice shelves are calm, vast expanses of nearly flat ice floating on dark water, complete ecosystems trapped between ice above and ocean below. Fact 24. The moment of calving. Calving, when ice breaks off from a glacier into water, is one of nature's most spectacular events. Sometimes it's quiet, a small chunk dropping into the water with barely a splash. But when large sections calve, especially from tidewater glaciers or ice shelves, it can be thunderous. The ice groans and cracks, sometimes for minutes before anything happens. Then, with sounds like gunshots or thunder, a section of ice face hundreds of feet high breaks away, tumbling into the water in slow motion, sending up huge waves and creating a boom that echoes for miles. These are moments when glacial time suddenly enters human time, when the slow transformation becomes visible and dramatic. After the initial splash, smaller pieces continue to break off for minutes, and the water remains churned and choppy, littered with ice fragments of every size. Fact 25. The speed demons. While most glaciers move imperceptibly, some are remarkably fast. Tidewater glaciers, those that terminate in the ocean, tend to move faster than land-terminating glaciers because the ocean provides less resistance than bedrock. The fastest glaciers in the world are found in Greenland and Antarctica. The Jakobshavn Glacier in Greenland was once measured moving at speeds up to 46 meters per day during a surge, that's nearly 17 kilometers per year. At such speeds, the ice doesn't just flow, it fractures and breaks, creating heavily crevassed surfaces that look more like broken shards than smooth ice. These fast glaciers are important contributors to sea level rise, rapidly transporting ice from land to ocean where it melts and adds to the ocean's volume. Fact 26. Glacier surges. Sometimes a glacier that has been moving at a steady, slow pace suddenly accelerates dramatically in what's called a glacier surge. During a surge, a glacier might move 10 to 100 times faster than normal, advancing several kilometers in just a few months or years. This happens when water accumulates at the glacier's base faster than it can drain away, essentially floating the ice on a layer of water and allowing it to slide forward with minimal resistance. Eventually the water drains, the surge ends, and the glacier returns to its normal pace. Surge-type glaciers are relatively rare, but they're impressive demonstrations of how even slight changes in conditions can dramatically alter ice behavior. After a surge, the glacier's surface is often chaotically broken, covered in crevasses and jumbled ice blocks. Fact 27. Not quite lifeless. It might seem impossible for anything to live on or within a glacier, but life finds a way even in these extreme environments. Microscopic organisms called cryoconite, from Greek words meaning cold and dust, live on glacier surfaces. These include bacteria, algae, fungi, and even tiny animals like tardigrades and ice worms. They survive in small pockets of melt on the ice surface, creating dark spots that absorb more sunlight and melt slightly deeper into the ice, forming their own microhabitats. Some of these organisms have antifreeze proteins that prevent ice crystals from forming in their cells. Others can enter dormant states when conditions become too harsh, reviving when conditions improve. These tiny communities represent some of the most extreme forms of life on Earth, thriving in a place most would consider uninhabitable. Fact 28. The snow algae's paint. In spring and summer, some glaciers develop a pink or red tint, as if someone has splashed watermelon juice across the snow. This is caused by snow algae, particularly a species called Chlamydomonas nivelis. These microscopic algae contain a red pigment that protects them from intense ultraviolet radiation at high altitudes. As they bloom across the snow surface, they can turn entire fields pink or red, a phenomenon sometimes called watermelon snow. While beautiful, this actually creates a feedback problem for the glacier. The darker color absorbs more heat from the sun than white snow would, accelerating melting. In areas where snow algae blooms are becoming more common, they're contributing to faster glacier loss, a reminder of how even the tiniest organisms can have large-scale effects. Fact 29. Iceworm's frozen world. One of the strangest glacier inhabitants is the iceworm, a small, dark worm that lives its entire life in ice. Found primarily on glaciers in the Pacific Northwest of North America, iceworms are one of the few animals on Earth that cannot survive outside of a very narrow temperature range near freezing. If the temperature rises above about 5 degrees Celsius (41 degrees Fahrenheit), they begin to die, literally melting into a puddle of cellular fluid. At night and in early morning, they emerge from within the ice to feed on algae and pollen on the snow surface. When the day warms, they burrow back down into the ice, traveling through cracks and pores. A single glacier might support millions of iceworms, forming a hidden ecosystem in the ice. They're a reminder that extreme is relative. To an iceworm, room temperature is as deadly as boiling water is to us. Fact 30. The glacier's edge. The edges of glaciers, where ice meets soil or vegetation, are called glacier margins, and they're ecologically fascinating places. Here, life is constantly colonizing newly exposed ground as the glacier retreats. The first colonizers are typically mosses and lichens, organisms that can survive on bare rock with minimal soil. They begin the slow process of breaking down rock into soil. Within a few years, small plants appear. Within decades, shrubs and eventually trees, depending on the location. Scientists can track this succession by dating the rocks and trees at different distances from the glacier, creating a timeline of ecological recovery. Some glacier forefields show 200 years of succession in the space of a few hundred meters, as if walking backward through time with each step away from the ice. Fact 31. The bears that never were. There's a common myth that polar bears and glaciers are closely connected, but polar bears actually don't live on glaciers. They live on sea ice, frozen ocean water, not on glacial ice, which forms on land. However, other creatures do use glaciers as habitat. Mountain goats in the Pacific Northwest occasionally cross glaciers to reach different areas. Arctic foxes den near glacier edges in Greenland. Seals haul out onto ice shelves to rest and give birth. Birds like snow petrels nest on ice-free rocks surrounded by glaciers. These animals are glacier-adjacent rather than glacier-dependent, using the ice environment opportunistically while maintaining their primary lives elsewhere. The glaciers themselves remain largely uninhabited by large animals. Their realm belongs to the microscopic, to organisms we cannot see with naked eyes. Fact 32. Pollen time capsules. Within glacial ice lies a record not just of atmosphere, but of vegetation. Pollen grains from plants, carried by wind, settle onto glaciers and become trapped in annual snow layers. These pollen grains are remarkably durable, with hard outer shells that can survive for thousands of years. By drilling ice cores and extracting pollen from different depths, scientists can determine what plants were growing in the region at different times in the past. An increase in pine pollen might indicate a warming period when forests expanded. Tundra plant pollen might indicate cooling. This creates a detailed history of vegetation change, and by extension, climate change. The ice preserves these tiny grains in chronological order, creating a timeline of the plant world stretching back millennia. Fact 33. Ancient air bubbles. Perhaps the most valuable scientific resource contained in glacial ice is air. When snow compresses into ice, small pockets of air get trapped and sealed off. These bubbles contain samples of ancient atmosphere, the exact mixture of gases that existed when the snow first fell. By drilling ice cores hundreds or thousands of meters deep and analyzing these bubbles, scientists can measure carbon dioxide, methane, and other gas concentrations from hundreds of thousands of years ago. This has provided crucial evidence about past climate change, showing clear connections between greenhouse gas levels and global temperatures. Each bubble is a tiny time capsule, preserving a breath of ancient air, waiting patiently in the ice to tell us about climates long past. Fact 34. The sound of ancient bubbles. There's something both scientific and magical about listening to glacial ice melt. As the ice warms, the ancient air bubbles trapped within begin to escape, making a gentle fizzing or crackling sound that's sometimes called Bergy seltzer, when coming from icebergs, or ice snap. It sounds remarkably like a carbonated drink being poured, 1,000 tiny pops as bubbles of air that were trapped when Rome was being built, or when mastodons walked North America, or even earlier, finally returned to the atmosphere. Scientists sometimes add chunks of glacial ice to their drinks, not just to cool them, but to listen to this sound, the music of ancient air returning to the world after millennia of imprisonment in ice. Fact 35. Microbes frozen in time. In the deepest, oldest ice, scientists have discovered living bacteria that have been frozen for hundreds of thousands of years. These microbes enter a state of suspended animation when frozen, with all their cellular processes stopped. When the ice is carefully melted in a laboratory, some of these ancient bacteria can actually revive and begin growing again. It's like they've been sleeping rather than truly frozen, waiting for conditions to improve. This raises fascinating questions about the nature of life and death. Are these bacteria alive while frozen? How long could they potentially remain viable? And could similar processes preserve life in the ice of other planets or moons? The discovery of such microbes has expanded our understanding of life's resilience and adaptability. Fact 36. Antarctica's frozen kingdom. The Antarctic ice sheet is Earth's largest single mass of ice, covering about 14 million square kilometers, roughly 1.5 times the size of the United States. It contains about 26.5 million cubic kilometers of ice, which represents approximately 90% of all the ice on Earth and about 70% of the world's fresh water. If this ice sheet were to melt completely, global sea levels would rise by about 58 meters, 190 feet, enough to submerge most coastal cities underwater. But this ice has been stable for millions of years. The ice in its center is over 800,000 years old in some places, possibly up to 1 million years old. To stand on the Antarctic ice sheet is to stand on a monument to stability, a frozen fortress that has witnessed countless human civilizations rise and fall without itself changing significantly, until now. Fact 37. The Dome of Accumulation. At the center of the Antarctic ice sheet is a place called Dome A, or Dome Argus. This is the highest point of the ice sheet, rising about 4,093 meters, 13,428 feet, above sea level, though most of this elevation is ice, not rock. The bedrock beneath is actually only about 600 meters above sea level. The rest is nearly 3,500 meters of ice stacked above it. At Dome A, temperatures are among the coldest on Earth, averaging about -58 degrees Celsius -72 degrees Fahrenheit, with winter temperatures dropping below -80 degrees Celsius -112 degrees Fahrenheit. The air is thin, the atmosphere is clear, and the ice beneath contains some of the oldest glacial ice accessible to science. It's one of the most remote and inhospitable places on the planet, reachable only by specialized expeditions, a place where the ice has accumulated grain by grain for nearly 1 million years. Fact 38. Greenland's smaller giant. Though smaller than Antarctica, The Greenland ice sheet is still immense, covering about 1.7 million square kilometers, roughly 80% of Greenland's land area. The ice is up to 3 kilometers, nearly 2 miles, thick in places, and if it were to melt completely, it would raise global sea levels by about 7 meters, 23 feet. Unlike Antarctica, which is a continent surrounded by ocean, Greenland is an island, and its ice sheet has more complex interactions with the surrounding seas. Greenland's glaciers flow more quickly than many Antarctic glaciers, especially those reaching the ocean, and the ice sheet is losing mass more rapidly than Antarctica. Despite this, it still contains enough water to drastically alter Earth's oceans, a slow-motion reservoir that has held its form for thousands of years but is now changing within human lifetimes. Fact 39. The weight that pushes down continents. The weight of ice sheets is so immense that it actually deforms the Earth's crust beneath them. Under Antarctica and Greenland, the land has been pushed down by the weight of ice, sometimes by more than a kilometer. The mantle beneath, the semi-molten rock layer under Earth's crust, flows slowly outward, squeezed away by the ice's pressure. If these ice sheets were to melt, the land would slowly rebound upward, a process that takes thousands of years. This is actually happening now in places where ice sheets have recently retreated. Scandinavia, for example, is still rising from the removal of the ice sheet that covered it during the last ice age, gaining about a centimeter per year in some areas. The land remembers the ice, and it slowly returns to its former shape, like a mattress slowly expanding after a weight is removed. Fact 40. Frozen mountain ranges. Beneath Antarctica's ice lies an entire landscape we cannot see, mountain ranges, valleys, lakes, and plains, all buried under ice. Some of these mountains are over 3,000 meters tall, but they're invisible from the surface because the ice covering them is even deeper. The Gamburtsev mountain range in East Antarctica is roughly the size of the European Alps, yet it was unknown until the 1950s because it's completely buried under ice up to 4,000 meters thick. Scientists map these subglacial features using ice-penetrating radar and other remote sensing techniques, creating ghostly images of a hidden world. Someday, if the climate changes enough, these mountains might emerge from the ice, seeing sunlight for the first time in millions of years. Fact 41. The dry valleys. In the midst of Antarctica, surrounded by ice, lie the McMurdo Dry Valleys, ice-free areas that are among the driest places on Earth. These valleys have seen no rain for nearly 2 million years. The extreme cold and low humidity cause any snow that falls to sublimate directly into vapor rather than melting. The valley's floors are covered in sand and gravel, and they're inhabited only by microscopic life in soils and rocks. The landscape looks remarkably like Mars, which is why NASA has tested Mars rovers there. Despite being in Antarctica, these valleys are so dry that nearby glaciers actually retreat rather than advance into them. The ice evaporates faster than it can flow forward. They're a reminder that extreme cold doesn't always mean ice and snow. Sometimes it means a frozen desert, barren and ancient. Fact 42. Ice streams, rivers within ice. Within the massive Antarctic ice sheet are features called ice streams, sections of ice that move much faster than the surrounding ice, like rivers of ice flowing through a frozen sea. These ice streams can be tens of kilometers wide and hundreds of kilometers long, and they move at speeds of hundreds of meters per year while the surrounding ice barely moves at all. They're like conveyor belts, rapidly transporting ice from the interior of the continent toward the ocean. What makes them move so fast is a combination of factors. The ice may be thinner there, the bedrock beneath may be smoother or covered in water or soft sediment, or the ice may be at the pressure melting point throughout. These ice streams are critically important because they control how quickly Antarctica loses ice to the ocean, acting as release valves for the entire ice sheet. Fact 43. The glacier's fingerprints. Every glacier leaves behind a unique signature in the landscape, like a fingerprint identifying exactly where ice once flowed. Scientists can look at a landscape and read its glacial history. The direction of striations tells which way ice moved. The size of erratics indicates how thick the ice was. The shape of valleys shows where the ice carved deepest. In places like the northeastern United States, you can still see evidence of ice sheets that retreated 15,000 years ago. The rounded hills, the scattered boulders, the thousands of lakes filling glacially carved depressions, all of these are the glacier's fingerprints, proof of its passage written in the land itself. These marks will persist for millions of years, long after we're gone, a permanent testament to the ice's power and patience. Fact 44. Earth's frozen cycles. Our planet has experienced many ice ages throughout its history, periods when ice sheets expanded to cover much more of the globe than they do today. The most recent series of ice ages, which we're technically still in, began about 2.6 million years ago. This period, called the Quaternary glaciation, consists of alternating glacial periods, when ice advances, and interglacial periods, when ice retreats. We're currently in an interglacial period that began about 11,700 years ago. During the last glacial maximum, about 20,000 years ago, ice sheets covered Canada, much of the northern United States, northern Europe, and parts of Asia. Sea levels were about 120 meters, 400 feet, lower than today because so much water was locked up in ice. The coastlines were completely different. You could walk from Siberia to Alaska, from Britain to France, across land that's now underwater. Fact 45. The Milankovitch cycles. These ice ages don't happen randomly. They follow predictable astronomical cycles discovered by Serbian scientist Milutin Milankovitch. Earth's orbit and orientation change in regular patterns over thousands of years. The shape of Earth's orbit around the Sun changes from more circular to more elliptical on a 100,000-year cycle. The tilt of Earth's axis varies between 22.1 and 24.5 degrees on a 41,000-year cycle. And Earth's axis wobbles like a spinning top on a 26,000-year cycle. These changes affect how much sunlight different parts of Earth receive during different seasons, which influences whether ice sheets grow or shrink. It's a cosmic dance, Earth's position in space conducting a symphony of ice, with movements spanning tens of thousands of years, predictable as clockwork yet powerful enough to reshape continents. Fact 46. The last glacial maximum. 20,000 years ago, during the last glacial maximum, Earth was a very different place. The Laurentide ice sheet covered nearly all of Canada and extended south into the northern United States, reaching as far as modern-day New York City and Seattle. In Europe, ice covered Scandinavia, Britain, and extended into Germany and Poland. The ice was kilometers thick. If you had stood in the location of modern Toronto, you would have been underneath nearly 3 kilometers of ice. The climate was colder everywhere. Even regions not covered by ice experienced tundra conditions where forests exist today. This was the world our ancient ancestors knew, a world where ice dominated, where coastlines were different, where migration routes between continents existed that are now submerged. Then, slowly, the ice began to retreat. Fact 47, the Great Melt. Starting about 19,000 years ago and accelerating around 14,000 years ago, the great ice sheets began to melt in what's called deglaciation. This wasn't a smooth process. There were periods of rapid melting interrupted by periods when the ice stabilized or even re-advanced. During the fastest melt periods, sea levels rose at rates of several meters per century, which sounds slow but was catastrophically fast for ecosystems and any human settlements near coasts. Meltwater carved enormous channels, created vast temporary lakes, and when ice dams holding these lakes failed, produced floods of almost unimaginable magnitude. The channeled scablands in Washington state were carved by such floods when glacial Lake Missoula repeatedly broke through its ice dam and drained in a matter of days, releasing more water than all current rivers on Earth combined, scouring channels hundreds of feet deep through solid basalt. Fact 48, frozen rivers through history. As ice sheets melted, they created massive rivers of meltwater that dwarfed anything we see today. The Mississippi River swelled to many times its current size, carrying meltwater from the retreating Laurentide ice sheet. For a time, meltwater drained through the St. Lawrence River Valley, but the land was still depressed from the weight of ice, creating a temporary outlet through other routes. These megarivers transported enormous amounts of sediment and fresh water into the oceans, potentially disrupting ocean circulation patterns and affecting global climate. The Amazon of ancient North America wasn't in the tropics but in the ice marginal zone, a braided system of channels carrying glacial meltwater toward the Gulf of Mexico, cloudy with suspended sediment, frigid even in summer. Fact 49, the Younger Dryas Mystery. About 12,900 years ago, just as Earth was warming and ice sheets were retreating steadily, something strange happened. Temperatures suddenly dropped again, especially in the northern hemisphere, and glaciers re-advanced. This cold snap, called the Younger Dryas, lasted about 1,300 years before abruptly ending and warming resuming. What caused it is still debated, but the leading theory involves fresh water from melting ice sheets disrupting the Atlantic Ocean circulation. This circulation, which includes the Gulf Stream, transports heat from the tropics to the North Atlantic. If too much fresh water enters the North Atlantic, it can shut down this circulation, causing regional cooling. The Younger Dryas is a reminder that climate can change suddenly, not just gradually, and that the slow melting of ice can trigger rapid changes elsewhere in the climate system. Fact 50, when mammoths walked. During the Ice Ages, glaciers shared the world with creatures now extinct. Woolly mammoths roamed the tundra and grasslands surrounding the ice sheets, their long hair and thick fat protecting them from brutal cold. Giant ground sloths lived in North America. Cave bears sheltered in European caves. Saber-toothed cats hunted in Ice Age grasslands. These animals adapted to the cold world, and when the ice retreated and climates warmed, many couldn't adapt to the changes. Within a few thousand years of the Ice Age ending, most of these large mammals were gone, victims of changing climate, changing vegetation, and increasing human hunting pressure. Some mammoths were so well preserved in permafrost that their remains, found thousands of years later, still had hair, skin, and stomach contents intact, time capsules from the Ice Age world. Fact 51. Early humans and ice. Our species, Homo sapiens, evolved during an ice age and spent most of our history living in an ice age world. The ice sheets shaped human evolution and migration. When sea levels were low, humans crossed from Asia to Australia, from Siberia to America, walking across land bridges now submerged. The ice sheets themselves were barriers. You couldn't simply walk across a kilometers-thick ice sheet, but their margins provided hunting opportunities and routes for migration. Early humans witnessed the retreat of the glaciers, watched landscapes transform within lifetimes, saw coastlines drown as seas rose. Some of humanity's oldest stories might be cultural memories of Ice Age events, passed down through thousands of years of oral tradition before being written down. Fact 52. Glacial refugia. During ice ages, as glaciers advanced and climates cooled, many species were pushed toward the equator or into small pockets of more favorable climate called refugia. These were areas that remained ice-free and relatively warm, valleys protected by mountains, coastal areas moderated by ocean currents, caves with stable temperatures. In these refugia, species survived periods of harsh climate, waiting for conditions to improve. When the ice retreated, these survivor populations expanded outward, recolonizing landscapes left barren by the ice. Genetic studies of modern species can identify these refugia by looking at where genetic diversity is highest. These are often the places where species weathered the ice ages, the source populations from which modern distributions expanded. Life's persistence through ice ages is a testament to its adaptability and resilience. Fact 53. Patagonia's southern ice. In southern South America, straddling the border between Chile and Argentina, lies the Patagonian ice field, the largest temperate ice field in the southern hemisphere outside Antarctica. It's actually two connected ice fields covering about 16,800 square kilometers, with ice up to 1,500 meters thick in places. From this ice field flow dozens of glaciers, many reaching down into forests or ending in fjords. The region receives enormous amounts of precipitation from Pacific storms, feeding the glaciers even though temperatures are relatively mild compared to polar regions. Some of these glaciers are advancing even as most glaciers worldwide retreat, a reminder that local conditions matter as much as global trends. The ice here is dramatic, crevassed surfaces, frequent calving events, and the strange sight of ice descending through forests, a meeting of ecosystems that seems impossible but is perfectly natural. Fact 54. Perito Moreno, the Equilibrium Glacier. Among Patagonia's many glaciers, one stands out, Perito Moreno Glacier. While most of the world's glaciers are retreating, Perito Moreno has remained relatively stable for decades, neither advancing nor retreating significantly. It's in equilibrium, with its gains roughly matching its losses. This 250 square kilometer glacier is famous for another reason. It periodically dams a lake, causing water levels to rise until the pressure breaks through the ice dam in a dramatic rupture. This cycle of damming and rupturing happens every few years, drawing thousands of spectators who watch and listen as the ice bridge collapses with thunderous cracks and groans. It's one of the few places where people can safely witness dramatic glacial events, standing on viewing platforms as house-sized chunks of ice break away and crash into the turquoise water below. Fact 55. Alaska's Tidewater Parade. Alaska hosts thousands of glaciers, including numerous tidewater glaciers that flow directly into the ocean. Glacier Bay, once completely filled with ice in the 1700s, is now a 100-kilometer-long fjord dotted with retreating glaciers at its arms. Cruise ships and kayakers navigate these waters, watching for calving events. The glaciers here are remarkably active. Hubbard Glacier, North America's largest tidewater glacier, occasionally surges forward, threatening to close off a fjord. Columbia Glacier, once stable, began a rapid retreat in the 1980s that continues today. Each glacier has its own personality, its own pace, its own relationship with the ocean. The sound of ice calving echoes across the water, sometimes sounding like distant thunder, sometimes like gunshots, always commanding attention from those lucky enough to witness it. Fact 56. The Himalayas' Third Pole. The Himalayas and surrounding mountain ranges contain the largest volume of ice outside the polar regions, earning the nickname the Third Pole. These high-altitude glaciers feed rivers that supply water to over 1 billion people in Asia. The Ganges, Indus, Brahmaputra, Mekong, and Yangtze rivers all originate from Himalayan glaciers and snowmelt. The glaciers here exist at much warmer temperatures than polar ice, surviving only because of the extreme altitude. Some glacier termini are at elevations above 4,000 meters where the air is thin and cold even in summer. These glaciers are now retreating rapidly, and their loss could have profound consequences for water security across Asia. They're a reminder that glaciers aren't just beautiful or scientifically interesting. For millions of people, they're the source of life itself, the slow-release reservoirs that provide water through hot, dry summers. Fact 57. Iceland's Fire and Ice. Iceland, despite its name, is only about 11% covered by glaciers. But those glaciers are extraordinary. They exist on an actively volcanic island, creating unique interactions between fire and ice. Vatnajökull, Europe's largest ice cap, covers several active volcanoes. When these volcanoes erupt beneath the ice, they melt enormous quantities of ice rapidly, creating glacial outburst floods called Jökullaups that can discharge more water than the Amazon River for brief periods. The meltwater bursts forth with tremendous force, carrying icebergs, boulders, and sediment, destroying roads and bridges, reshaping the landscape in hours. These events are terrifying and spectacular, a reminder that glaciers aren't just slow and steady, but can become agents of rapid, catastrophic change when the right conditions occur. Fact 58. Tropical glaciers' last stand. Glaciers exist even near the equator, in the highest mountains of East Africa, South America, and New Guinea. These tropical glaciers are rare and rapidly disappearing. Mount Kilimanjaro in Tanzania has lost more than 80% of its ice cap since 1912. The glaciers of the Andes in Ecuador and Peru are shrinking. New Guinea's Puncak Jaya Glacier has retreated dramatically. These glaciers survive despite tropical heat because they exist at elevations above 4,500 to 5,000 meters where temperatures remain below freezing year-round. But they're especially vulnerable to warming because even small temperature increases can push them over the threshold from year-round freezing to seasonal melting. Within decades, many of these tropical glaciers may vanish entirely, taking with them water sources for communities and closing the book on glaciers that have existed for thousands of years. Fact 59. Norway's fjord makers. Norway's coastline is famous for its fjords, long, narrow inlets with steep walls that penetrate far inland. These are glacially carved valleys that flooded with seawater when Ice Age glaciers retreated and sea levels rose. The fjords are incredibly deep. Sonefjord, Norway's longest and deepest, extends 205 kilometers inland and reaches depths of 1,308 meters, deeper than the mountains are tall. This depth shows how powerfully glaciers carve through the rock. The fjord walls rise nearly vertically from the water, sometimes with waterfalls plunging directly into the sea, the whole landscape seeming almost too dramatic to be natural. Yet it is natural, carved grain by ice that flowed here for thousands of years, then released the ocean into its deepest cuts, creating a landscape of profound beauty that draws visitors from around the world. Fact 60. The Alps' retreating crown. The European Alps contain about 4,000 glaciers, though many are small and retreating rapidly. These were the glaciers that first inspired scientific study of ice, where scientists first recognized that ice sheets had once been much larger, where the concept of ice ages was developed. The Aletsch Glacier, the Alps' largest, stretches 23 kilometers and contains about 11 billion cubic meters of ice. These glaciers have been measured and photographed for over a century, providing some of the best documentation of glacier change anywhere in the world. Old photographs show ice extending far down valleys, with hotels and hiking trails approaching glacier snouts that have now retreated kilometers uphill. The glaciers are still there, still beautiful, still drawing skiers and hikers, but they're shadows of their former selves, smaller every year, glacial ghosts fading slowly from Europe's highest mountains. Fact 61. New Zealand's southern ice. On the South Island of New Zealand, the Southern Alps host several substantial glaciers despite the relatively warm maritime climate. Franz Josef and Fox glaciers are unique. They descend from high peaks down to near sea level, flowing through temperate rainforest zones. You can literally walk from subtropical forest to glacier ice in less than an hour. These glaciers exist because of enormous precipitation from storms rolling off the Tasman Sea. Some areas receive over 10 meters of rain and snow annually, feeding the glaciers faster than the mild temperatures can melt them. Like many glaciers worldwide, they've been retreating in recent decades, but their situation is complex, with periods of advance and retreat depending on precipitation patterns. They remain dramatic features, white ice descending through green forest, a juxtaposition that seems impossible until you see it yourself. Fact 62. Reading ice cores. When scientists drill ice cores, they're creating a time machine. A core drilled from the center of Antarctica or Greenland can be over 3 kilometers long and contain ice up to 800,000 years old. The core is carefully extracted in sections, kept frozen, and transported to laboratories where it's analyzed in dozens of ways. Scientists measure the ratio of different oxygen isotopes in the ice to determine past temperatures. They analyze trapped air bubbles to measure ancient atmospheric composition. They look for volcanic ash layers to date eruptions and use them as chronological markers. They examine dust and pollen to understand past vegetation and atmospheric circulation. They measure electrical conductivity to identify volcanic eruptions. Each meter of core contains multiple years or even decades of accumulated snow, creating a timeline of Earth's climate with extraordinary detail. Fact 63. The ice's annual rings. Just as trees have growth rings, glaciers have annual layers visible in ice cores. In polar regions where there's a distinct seasonal cycle of accumulation, each year's snowfall creates a layer that can be distinguished from the layers above and below. These layers vary in thickness depending on how much snow fell that year, creating a record of precipitation. They also show seasonal variations in chemistry. Summer snow differs slightly from winter snow in isotopic composition and impurities. Scientists can count these layers like tree rings to establish chronology, though it becomes increasingly difficult deeper in the ice where layers are compressed thinner and thinner. In some ice cores, scientists have counted back more than 100,000 annual layers, each one representing 1 year in Earth's ancient past, a patience that took decades of painstaking work. Fact 64. Temperature stories and isotopes. The ratio of different oxygen isotopes in glacial ice provides a thermometer for past climates. Water molecules can contain different isotopes of oxygen, most commonly oxygen-16, but also heavier oxygen-18. When water evaporates from the ocean, molecules with lighter oxygen-16 evaporate slightly more easily. When water vapor cools and forms precipitation, molecules with heavier oxygen-18 condense out slightly more easily. This means that snow falling in colder conditions has a different isotope ratio than snow falling in warmer conditions. By measuring these ratios in ice core layers, scientists can estimate what the temperature was when that snow fell, creating a temperature record stretching back hundreds of thousands of years. This technique has revealed the pattern of ice ages and interglacial periods, showing us that our current climate, though changing, is not unprecedented but part of a larger pattern. Fact 65. Volcanic signals in ice. Ice cores contain evidence of volcanic eruptions from around the world. When volcanoes erupt explosively, they inject sulfur compounds high into the stratosphere where they can circulate globally and eventually fall back to Earth in snow and rain. In ice cores, these sulfur spikes appear as distinctive layers that can be chemically analyzed to identify which volcano produced them. This creates a global volcanic record going back tens of thousands of years, including eruptions that occurred before written history. By matching these signals between ice cores from different locations, scientists can establish synchronous time markers, events that happen at the same time everywhere, helping to align different climate records. Some layers come from eruptions we know about from historical records, but others record supervolcanic eruptions from deep in prehistory that humans have no memory of. Fact 66. The Holocene, our interglacial home. The current interglacial period, which began about 11,700 years ago, is called the Holocene. This is the geological epoch during which all of human civilization has developed. The climate during the Holocene has been relatively stable compared to the wild swings of Ice Age conditions. Temperature variations have been measured in fractions of a degree rather than tens of degrees. This stability provided the predictable conditions that allowed agriculture to develop independently in multiple regions. Reliable seasons, stable coastlines, and moderate temperatures created the environment in which cities could be built, trade routes established, and complex societies developed. The entire story of human civilization, from the first farming villages to modern cities, has unfolded during this relatively warm, stable interglacial period. We are creatures of the Holocene, adapted to and dependent on its particular conditions. Fact 67, Mass Balance, the glacier's health check. Glaciologists measure glacier health through mass balance, the difference between accumulation, snow and ice gained, and ablation, snow and ice lost. A glacier with positive mass balance is growing, one with negative mass balance is shrinking. Measuring this requires patient work. Scientists drill stakes into the glacier at various elevations and return periodically to measure how much ice has been gained or lost at each location. They dig snow pits to measure how much snow accumulated over winter. They use weather stations to track temperature, precipitation, and solar radiation. This data, collected year after year, creates a detailed record of each glacier's response to climate. Most glaciers worldwide currently have negative mass balance. They're losing more ice than they gain each year, a clear signal of warming climate. But there are exceptions, reminders that local conditions matter and that glaciers respond to more than just temperature. Fact 68. The albedo effect. One reason glaciers are so important to climate is their color. White snow and ice reflect most incoming sunlight back to space, typically 80 to 90% of it. This is called high albedo. Dark surfaces like soil, rock, or ocean water absorb most sunlight, typically 80 to 90% of it, low albedo. When glaciers melt, they expose darker ground or water beneath, which absorbs more heat, which causes more warming, which causes more melting. This is a positive feedback loop, meaning it reinforces itself. The albedo effect is part of why polar regions are warming faster than the global average. As ice retreats, darker surfaces absorb more heat, accelerating the warming. It's also why snow algae, which darken snow surfaces slightly, can accelerate melting. Color matters in the climate system, and the bright white of glaciers has a cooling influence that diminishes as they shrink. Fact 69. Glacial earthquakes. When large icebergs come from glaciers, they don't just make local noise, they can create seismic waves strong enough to be detected by earthquake monitors thousands of kilometers away. These glacial earthquakes were first recognized as a distinct phenomenon in the early 2000s. They typically last 20 to 50 seconds, much longer than most tectonic earthquakes of similar magnitude. The seismic signal is caused by the massive force of ice hitting water and the glacier's response to suddenly losing a large section. The remaining ice shifts, adjusts, and settles into a new configuration. By monitoring these glacial earthquakes, scientists can track calving events at remote glaciers without having to observe them directly. The number and magnitude of glacial earthquakes have increased at some Greenland glaciers in recent decades, providing another line of evidence for accelerating ice loss. Fact 70. The frozen reservoir. Glaciers and ice sheets contain about 69% of all fresh water on Earth. To put this in perspective, all the rivers and lakes in the world combined hold only about 0.3% of fresh water. Most of the rest is groundwater. This means that most of the water you could drink, wash with, or water crops with exists as ice, primarily in Antarctica and Greenland. During ice ages, even more water was locked up in ice, which is why sea levels were so much lower. Glaciers are effectively frozen reservoirs, holding vast amounts of water that would otherwise be in the ocean. As they melt, they transfer this water from land to sea, raising sea levels. For countries that get their water from glacially fed rivers, the glaciers act as natural water towers, storing winter precipitation as ice and releasing it gradually through summer, providing water when it's needed most. Fact 71. The slow journey to the sea. A water molecule that falls as snow on the center of Antarctica faces a journey that can take tens of thousands of years to complete. First, it must be compressed into ice, a process that takes decades. Then, buried under successive snowfalls, it must travel with the ice as it flows slowly toward the coast. The ice moves only a few meters per year in the interior, perhaps faster as it approaches the coast and joins ice streams. If the molecule is near the bottom of the ice sheet, it might travel for 100,000 years before reaching the ocean. If it's near the top, perhaps only a few thousand years. But eventually, unless it sublimates back into the atmosphere, it will complete its journey, either calving off in an iceberg, melting at the glacier's base, or melting on the surface and flowing through the ice to the ocean. It's the slowest water cycle on Earth, a journey measured in geological time. Fact 72. Meltwater streams and their music. On warm summer days, glaciers come alive with the sound of running water. Meltwater streams flow across the ice surface, finding pathways through crevasses, carving channels in the ice, creating braided networks that change daily. These streams are remarkably clear at first, pure meltwater from melting ice. But as they flow, they pick up sediment, gradually turning milky with glacial flour. The sound of these streams is distinctly musical, higher pitched than typical rivers because they're flowing over and through ice rather than rock. The water is extremely cold, just barely above freezing, and it flows with vigor, driven by the subtle slopes of the ice surface. On some glaciers, you can watch these streams vanish into moulins, hear the water roaring as it plunges into darkness, feel the mist rising from below. It's a reminder that glaciers, though made of solid ice, are intimately connected to liquid water. Fact 73. Glacial lake outburst floods. Sometimes glaciers create lakes, either by damming valleys with ice or by melting and leaving water-filled depressions. These glacial lakes can be peaceful for years or decades, but they're potentially dangerous. If the ice dam weakens or the lake fills beyond the dam's strength, it can fail catastrophically, releasing the entire lake in a few hours or days. These glacial lake outburst floods, or GLOFs, can carry enormous volumes of water and debris downstream, devastating everything in their path. In the Himalayas, GLOFs are an increasing hazard as glaciers retreat and create new, unstable lakes at high altitudes. In Iceland, where volcanoes can melt ice rapidly from below, Jökulhlaups can release the equivalent of several Amazon rivers for brief periods. These events are reminders that glaciers can create sudden, violent events even though they normally move with almost geological slowness. Fact 74. The glacial milk rivers. Rivers flowing from glaciers carry so much suspended sediment that they're often opaque, colored in shades from pale gray-blue to turquoise to muddy gray. This glacial flour never seems to settle. The particles are so fine they can stay suspended for days. When these rivers enter lakes or the ocean, they create distinctive plumes visible from space, pale threads winding through darker water. The sediment eventually settles out, but it can travel hundreds of kilometers first. Over geological time, this sediment builds up, creating vast plains of glacial till and filling ocean basins. The Columbia River in the Pacific Northwest, fed partly by glaciers in the Canadian Rockies, delivers about 10 million tons of sediment to the Pacific each year, the ground-up remains of mountains, carried grain by grain to the sea, never to return. This is erosion in action, the slow dismantling of mountain ranges particle by particle. Fact 75. Ice and ocean currents. The melting of glaciers doesn't just add water to the ocean, it affects ocean circulation patterns. The thermohaline circulation, sometimes called the global ocean conveyor belt, is driven by differences in water temperature and salinity. Cold, salty water is denser and sinks, driving deep ocean currents. If large amounts of fresh water from melting ice sheets enter the ocean, they can reduce salinity and disrupt this circulation. This is thought to have happened during the Younger Dryas, when massive amounts of glacial meltwater entered the North Atlantic, potentially shutting down the circulation that brings warm water northward. Currently, scientists are monitoring whether accelerating ice sheet melt might be starting to weaken the Atlantic circulation. It's a reminder that the cryosphere, the frozen parts of Earth, is not separate from the rest of the climate system but intimately connected to ocean and atmosphere. Fact 76. The chemistry of ancient ice. Ice cores don't just record temperature and atmospheric composition, they contain traces of human history. In Greenland ice cores, scientists have found evidence of ancient air pollution. There's a spike in lead concentrations from Roman times, when lead smelting for silver and pewter released lead into the atmosphere that eventually settled in Greenland snow. This pollution decreased when the Roman Empire fell, then increased again with medieval and Renaissance mining. There are signatures of major wars, sulfate from burning forests, particulates from industrial activity. The Clean Air Act shows up as a decrease in sulfate pollution. In Antarctic ice, there's a layer of radioactive isotopes from nuclear weapons testing in the 1950s and 1960s. These traces are tiny, but they're there, proof that even remote glaciers record human activities, that our actions have reached the ends of the Earth and left permanent marks in the ice. Fact 77. The blue planet's whitecaps. From space, Earth's ice sheets are among the most distinctive features, bright white caps at the poles, standing out against blue ocean and multicolored continents. These white caps play a crucial role in Earth's energy balance. Without them, Earth would absorb significantly more solar energy, warming considerably. The ice sheets are like air conditioners for the planet, helping to maintain moderate temperatures. This is why their shrinking is concerning. It's not just that melting ice raises sea levels, but that the loss of reflective ice surface accelerates warming. Astronauts often comment on how fragile Earth looks from space, how thin the atmosphere appears, how precious the ice caps seem. Seeing the whole planet at once makes it clear that ice sheets, though remote from most human habitation, are integral to the system that makes Earth livable. Fact 78. Glaciers' gift of water timing. In regions with wet winters and dry summers, like parts of the Western Americas and Central Asia, glaciers provide a crucial service: water timing. Snow falls in winter, is stored as ice, and melts gradually through summer when water is needed most for agriculture. Rivers fed by glaciers maintain higher flows through late summer than rivers fed only by rainfall. This natural storage and release system has sustained communities for millennia. But as glaciers shrink, their storage capacity decreases, and they release water earlier in the year. Eventually, when glaciers become very small, they no longer provide substantial summer water, and the river's late summer flows decrease. This is already happening in some regions, where glacier-fed rivers are becoming less so each year, their flows peaking earlier and dropping lower by late summer. The water hasn't disappeared, it's just arriving at different times, requiring human adaptation and water management strategies to cope with the change. Fact 79. Sacred ice mountains. Many cultures hold glaciers and ice-covered mountains sacred. In Peru, the Quechua people view glaciers as apu, mountain deities that provide water and protection. The retreat of these glaciers is not just an environmental concern but a spiritual crisis. In the Himalayas, several peaks including Everest are considered sacred in Buddhism and Hinduism, believed to be homes of gods. Local communities make offerings to mountain spirits before climbing expeditions. In Alaska, indigenous Tlingit people have traditional names and stories for glaciers that have been part of their landscape for thousands of years. These cultural relationships with ice remind us that glaciers aren't just physical features but have deep meaning for the people who live near them, woven into origin stories, spiritual practices, and cultural identity. Fact 80. The explorers of ice. Human fascination with glaciers has driven exploration for centuries. In the 1700s, European scientists began systematically studying alpine glaciers, making measurements and noticing evidence that ice had once been far more extensive. In the 1800s, the quest to reach the poles became an obsession, with expeditions battling through ice-choked seas and crossing vast ice sheets. Names like Ernest Shackleton, Robert Scott, and Roald Amundsen became legendary for their polar expeditions. These explorers faced unimaginable hardships, temperatures far below zero, months of darkness, crevasses that could swallow a man, fierce winds, and isolation. Some succeeded, others died trying. Their journals describe landscapes of surreal beauty and terrible harshness, ice stretching to every horizon, a world that seemed hostile to human life yet drew them irresistibly forward. Fact 81. Otzi, the glacier's gift to archaeology. In 1991, hikers in the Alps discovered a body emerging from melting ice. At first thought to be a modern mountaineering victim, it was soon revealed to be a man who died about 5,300 years ago. Otzi the Iceman, as he became known, was preserved in ice so perfectly that his clothes, tools, stomach contents, and even tattoos survived. He was carrying a copper axe, arrows, and a partially constructed bow. Analysis showed he had eaten ibex and deer meat shortly before his death, and that he died from an arrow wound to the shoulder, likely murdered. Otzi provides an unprecedented glimpse into Copper Age life. We know what people wore, what they ate, what tools they used, even what diseases they suffered from. He's one of many archaeological finds released by melting glaciers, remnants of past human lives preserved in ice, waiting thousands of years to tell their stories. That's the end of our journey to the glaciers. Have good night and don't forget to subscribe your channel for more video like this.